but with shapes as opposed to with functions. So it says to work with a partner, and it says graphs of 8 basic parent functions are shown below. Classify each function as constant, linear, absolute value, quadratic, square root, cubic, reciprocal, or exponential. In the interest of time, I'm not going to have you group up for this one, but I do want to have some participation if you know what's going on with these. So a V-shaped graph. I know you've all seen this, at least back in Algebra 1. If you don't exactly remember which one creates this, that's fine. Does anybody remember? Yeah, it's absolute value. I was going to say, if you don't remember, I'll give you a hint. It's what we worked on yesterday. This is an absolute value graph. Absolute values create V-shaped graphs. So A would be absolute value. And when we're talking about parent function, a parent function is the most basic way of writing a particular function. And so what we're going to be doing here, and by the way, we will be using function notation in this class. So instead of writing y equals, we're going to be saying f of x instead of y. It means the same thing. You saw function notation back in Algebra 1. It isn't used all that often in Algebra 1 necessarily. It will be used a lot here. Instead of y equals, we just use f of x. So these two letters basically take the place of y. And this is going to equal the absolute value of x, because that is the most basic way to write an absolute value function, is just absolute value of that variable. For b, does anybody have any idea what b represents based on this list up top here? Constant means it's exactly the same all the way through. Is that the same all the way through? No. Okay. Linear means it's a straight line. Is that a straight line? No. Absolute value would be a V-shaped graph. Definitely not that. Quadratic, I think you all know that one. That would be the parabola. That's the U-shaped graph. Definitely not U-shaped. So then we're dealing with either square root, cubic, reciprocal, or exponential. Does anybody know which of those 4 this would be? So this is kind of, it's almost like the opposite of an exponential. Exponential usually starts low and then shoots up really quick later, which we'll see later. This one is kind of like the upside, almost an upside down version of exponential. So let me ask you this. X squared would start low and then shoot up very quickly. What's the opposite operation, the inverse operation of squaring something? Square root. There you go. So square root. And in terms of the function, we would say f of x. And we're talking about parent functions here. So these are the most basic form. We would just say square root of x. All right, now the next one, C. This one technically could count in 2 categories, because a constant is linear. Every constant is linear, but not every linear is constant. But we're going to call this one constant. So yes, it is also linear, but it is constant. Constant meaning there isn't a slope. Like with linear equations, you have a slope, y equals mx plus b kind of stuff. M would be the slope, but there's no slope here because it's a horizontal line, which means the slope is 0. So when you say f of x, you're not going to have an x over here. This is the type where it's just equal to a number in terms of how far it is up from the from the middle of the graph, basically the y-intercept. Where does this line cross the y-axis? How far up is it? 1. So f of x equals 1. That's the equation for that. This is stuff that you also saw in Algebra 1. All right, the next one, D. Jared, I'll go back to you on this one. Exponential, there it is. So we got exponential. Nice. And this one is, I misled you a little bit because I said x squared. Exponential is actually kind of the base value and the exponent are kind of opposite on this one. So it's not x squared, it's actually f of x is equal 2 to the x. Instead of x squared, the base and the exponent have swapped spots. The exponential would be f of x equals 2 to the x power. And that would be the parent function for an exponential. Because x squared is a quadratic, and that one's going to show up later. How about E? Yeah, E is cubic. Yep. You had limited options on qubit, not qubit, cubic. You had limited options on this one because we still have linear and quadratic, meaning those ones aren't going to be this one because I think we know what those look like. So it's either going to be cubic or reciprocal. This one is cubic, which would be to the power of 3. So this is f of x is equal to x to the power of 3, or x cubed, x to the third power. F, and everybody said for F, linear. All right, well, not everybody, 2 people. Okay, linear. F of x equals x. One of the most basic forms of a function you can possibly have. F of x is equal to x. Slope of 1, y-intercept of 0, up 1 over 1 from the origin. All right, G. Of the 2 that are left, which one does this have to be for G? It's got to be reciprocal. Because H is the parabola, which would be quadratic. So let's see, reciprocal. What does reciprocal mean? Anybody remember? What does the word reciprocal mean in terms of math? We multiplied by reciprocals the other day, last week a little bit, Jared. Are you thinking opposite reciprocal? So like positive and negative and then flipped over? So if you do both at the same time, in terms of a linear function, you'd be dealing with perpendicular lines. However, reciprocal is just straight flip it over. So if you have your linear function of x, if you take the reciprocal of x and you make it a fraction, how would that be written? You can make any number a fraction by doing what? Putting a 1 over it, right? So f of x is equal to 1 over x. It's the reciprocal of the basic linear function. So turn it into a fraction, flip it over, which basically means if it's a whole value, you put a 1 over it. So f of x is equal to 1 over x. And then the last one is quadratic. Our good old friend, the parabola. This is probably the last thing that you learned in Algebra 1. And this would be f of x is equal to x squared. All right. So every other form or any other equation or function that is written based off of one of these parent functions would be considered a transformation of that original function. So if you have a quadratic that has x squared in it with other numbers involved, that would be a transformation because it would be a quadratic, but it would not be that quadratic. It'd be a quadratic somewhere else on the graph. And when you start moving things around, that is what's considered a transformation. So go ahead and flip the page over. So what you're going to end up doing here is for identifying the function families, it says write each parent function under its graph, and to use a graphing calculator to check. Again, we're going to do a lot of this just as a class here real quick. I don't have enough graphing calculators for everybody yet. So we'll talk about domain and range and all that kind of stuff as well. I'll remind you about that. So it says identifying function families. Functions that belong to the same family share key characteristics. The parent function is the most basic function in a family. Functions in the same family are transformations of the parent function. So all that stuff is stuff that I already said about what's on the first page. So the core concepts, it says some parent functions we will study this chapter. So those ones. So the first function here is a constant function. And that would be f of x equals 1. And we're just going to be talking about, actually, problem 1 there. Yeah, we don't really need to worry about that. We already did that on the front, so we're good. All right. A constant function is just some value of y, and that's it. There is no slope or anything like that. Does anybody remember what domain and range means? So you got like values of the domain and values of the range, and it has to do with what the graph looks like and all that kind of stuff. All right. Let's see if this refreshes any memories. Domain are the x values. Does that sound familiar? So all possible values of x would be the values of the domain. And if you're using a table of values, these would be the inputs. Those are the numbers that you would plug in for X. So now that we have domain, somebody help me out with range. Let's define that real quick. What else do we have on the graph? What's that? Y values, yeah. So the range would be the possible Y values. And on a table of values, those wouldn't be the inputs, they'd be the what? The outputs, yeah. I would be willing to guess that you've seen this kind of stuff in your science class or one of your science classes, right? Input, output, table of values, making graphs out of those things. All right. So possible values for X on our domain. The lines there mean it extends in both directions forever. So what are our possible values for X? If it goes positive and negative forever, or negative and positive forever, what would be our possible values for X? Anything? Yeah, it could be anything. And any number, something that you probably learned in Algebra 1 would be the phrase all real numbers. Does anybody remember that from Algebra 1 when you're talking about domain and range? Okay. All real numbers. So you could write all real numbers, or we do have a symbol for it if you don't want to write that sentence. It's a capital R with two vertical lines on the left. That just means all real numbers. So any number that you could possibly think of would be an X value because it goes forever negative and it goes forever positive. What about the range though on this one? Does this graph go up or down at all? No. So what is our Y value? Looks like it's up a little bit. What was it on the front? What did we write for our parent function of constant? F of X was what? Equals 1. Yeah, so we're just say Y equals 1. Because the only value for Y there is 1. There are no other values for Y. That's it. All right, for linear. Does this one go left and right forever? Even though it's diagonal, does it still go negative and positive on the X value or X axis forever? Okay, so all real numbers. What about the Y values this time? Does it go up forever? Does it go down forever? Yeah, so what are we going to write for Y values? All real numbers again. Yeah, same thing. So linear equations will have all real numbers for both domain and range. Absolute value. Let's see. What would our domain be for absolute value? Does it continue negative forever on the x-axis? That arrow, does that keep going left forever? Okay, what about going right forever? Yeah, all right, so domain, all real numbers. I think I see a pattern developing through the domain. And then the range, does this go up forever? Yeah, does it go down forever? No. Where does it stop? 0, okay. So all of our Y values would be greater than or equal to 0, right? Jared? Where? On the Y? Where? Like, oh, this is the axis. Sorry. This is the Y-axis. This is the graph. Okay. I know the Y-axis is usually a little bit more distinct. The X and the Y-axis are usually more distinct than that. Tell you what, I will grab. How about this? Yeah, those are the graphs. Okay. All right, so we got Y is greater than or equal to 0. So the ranges will change depending on what's happening, but it looks like the domains are pretty much all the same. What do we think the domain is for quadratic? All real numbers, yeah. Because it's going left and right forever. This one definitely happens more slowly than the rest of them, but because of the arrow and because there is still a bit of a slant going to the positive and negative direction on the x-axis, it is still all real numbers. And then how about the range here? Yeah, it's the same as the absolute value one. Y is greater than or equal to 0. Because it starts up here, comes all the way down, goes to 0 on the y-axis, and then turns back around and goes back up. So all the values of y are either 0 or more than 0. Cool. So these are our domains and range of our function families that we're going to be focusing on in this first chapter, in this first unit. So what we're going to be talking about over the next like page and a half-ish, or probably the rest of it actually, are transformations. And so if you're identifying a function family, first of all, this is a V-shaped graph, so this has to be absolute value, no matter what. V-shaped graphs are always absolute value. And so it says to identify the function family to which f belongs, that function would be the absolute value family. And then you're going to compare the graph of f to the graph of its parent function. So it tells you what the actual graph is here. It gives you the function here. It says 2 times the absolute value of x plus 1. If we looked at the basic parent function, go ahead and put this on here as well. I'm going to graph the parent function on here. Just got to make sure it doesn't show up on the next page, because maybe it does. No, it does not. Okay. So let's get our parent function on here. The parent function of the absolute value of x is basically just a straight line with a slope of 1 or -1 coming in from the left. So if you just go up 1 and back 1 going that direction, and then if we move this direction, it would be up 1 and over 1. And I can see that we're missing a couple of points on there, but just go ahead and estimate where those might be at. Don't worry too much about a ruler right now. You can just kind of make this as straight as you possibly can. Doesn't need to be perfect. We're just doing some sketches right now. And so that would be our parent function. This would be f of x is equal to the absolute value of x. And so the transformed function is the one that was already there. It would be f of x is equal to 2 times the absolute value of x plus 1. What has changed between the parent function and this function here? So somebody just give me some like regular language to describe what's happening here. What's that? Looks like it went up 1 to me. So the original to this one here. Yeah. So if we're going back to the original, yeah, it would be down 1. But it looks like it went up 1, right? Do you see anywhere on there on that equation where 1 is being added? Yeah, right? This right here. So this plus 1, we can make a little bit of an assumption right now that this plus 1 probably means that it moved the original one up 1. Okay. What else is a little bit different? It's more narrow, yeah. So if you look at the opening here for the original one versus this one, it's definitely more narrow than it was. And Jared, you're saying that means that this is the narrowing of the graph. Yeah, exactly. So instead of up 1 over 1, it's going up 2 over 1. So this number here is it isn't slope, but it is basically the absolute value equivalent of slope. And the reason why it can't be slope is because it's not linear. But it's -2 going this way, or yeah, coming down from here, it's -2, and +2 going up this way. Whereas this one was -1 coming down this way, and +1 going up this way. So it basically makes it narrow. That number, as it gets further away from 0, is going to make that graph narrower. And then this change over here is going to move that y value. Could move it down as well. If there's a minus, it would have moved it down. All right, let's go to page 2. Yeah. What do you mean, how do you find it? Got it. The parent function is always the most basic form. So right here, these are the parent functions of those different types of graphs. So f of x equals x is the parent linear function. F of x equals the absolute value of x is the parent absolute value function. So it's basically just x with those types of graphs. Or in this case, constant would be 1 because it doesn't have a slope. All right, check out this next one here. I'm going to go ahead and draw the parent function on here, but I want you to identify, first of all, what function are we looking at here? What type of family? What is it? Quadratic, yeah. So we definitely have quadratic. That's a quadratic. And then it says compare the graph of f to the graph of its parent function. So the parent function, I'm going to go ahead and put this on here so we can see it. And that would be here. And then the next one would be here. So actually, yeah. All right. So it looks like this. This is our basic parent parabola. That would be f of x is equal to x squared. So, descriptors on what's happening here. How can we describe what's going on? Yeah, so it's wider. And I'm going to say due to the 1/4. Why does it do that? It actually is just the opposite of what you were telling me with the absolute value. So with absolute, or it doesn't matter if it's absolute value or quadratic. If the number gets further away from 0, so like 2 or 3 or 4, it's going to make it narrow. If the number gets closer to 0 from 1, sorry, I guess I should start from a starting point. From 1, if it gets further away from 1, or it gets further away from, I guess 0 works too. But if you start at 1 and it gets further away from 0, it's going to get narrower. If you start at 1 and you get closer to 0, like 1/4, because 1/4 is closer to 0 than 1 is, it'll actually make it wider. So the closer you get to 0, the wider it opens. And the reason for that is basically, if you think about how squared works, like squared is going to increase pretty much exponentially, right? And so by tempering that exponential increase, you're decreasing the amount by which it's increasing each time, which makes the curve a little bit shallower. If you multiply it by a larger number than 1, that's going to increase the rate at which it's going up in terms of the quadratic. So making it narrow. So it'll increase faster the larger this number gets away from 0. It's not necessarily the smaller this number gets, it's the closer it gets to 0. Because it could be negative. Negative could still be really narrow, it just gets 10. So it's gotten wider due to the 1/4 because that means it's closer to 0. What else is happening here? What else did it do? So here's our vertex, right? The bottom point. Here's the vertex of this one. So where is it gone? What's that? Gone to 3. That's moved to the right 3 spaces. And there's a 3 right there. Because when you're dealing with, forget the exact explanation to be honest, but I know that when you're dealing with this type of particular graph, you're going to learn something called vertex form probably a little bit later on. And with vertex form, you put your x value in parentheses. The subtraction is kind of the opposite of how you would think about it. So if it was a plus, it would actually move to the left. But if it's a minus, it would move to the right. Mathematically, it works out because when you type in the numbers are going to work. Again, I'm forgetting exactly why that happens every single time, but mathematically it works out, which is just going to be my basic explanation of why for now. But it's moved 3 to the right. So 3 to the right. And that's because of this x minus 3. All right. So let's keep going. In terms of describing transformations, transformation basically changes anything about the parent function. That could be size, shape, position, orientation. A translation is a transformation that shifts the graph horizontally and or vertically, but does not change its size, shape, or orientation. So here's the thing. There's a difference between a transformation or a translation. So a transformation, once again, changes the size, shape, position, or orientation of a graph. A translation is a type of transformation. So it's a more limited type of transformation. It's annoying that the words are so similar. I'm not going to lie about that. Transformation versus translation. But a translation basically just moves the graph. Okay. Translation does something like this. The shape of the graph, the width of the graph doesn't change. But where it is on the graph moves around. So it's like up, down, left, or right. Whereas up here, this would be a transformation because it changed the width of it. It not only changed the width, but it also changed where it was. So over here, it says to graph f of x, or g of x. By the way, you don't have to use f every time. You can use a different letter. F, G, H are probably the most common letters you will see to describe what a function is. And the reason why there are other letters is because sometimes you will graph multiple functions on the same graph, and you can't always use F for function. And so the two next letters in the alphabet would be G and H. So F uses function notation, G uses function notation, H as well. So this says here to graph G of x is equal to x minus 4. And its parent function, and then describe the transformation. So let's go ahead and just get regular old parent function on here. That would be, we're going to call that f of x is equal to x. And I'm just going to go ahead and put this on here. So our regular parent function, we're doing this one first, starts at the origin. I'm going to write that as well. That's f of x is equal to x. Would this be... What type of graph would this be, first of all? What family is this part of? Linear. Yeah, it's this one right here. F of x equals x. So that'd be linear. Constant didn't have x on the right side. Constant was just a number. So the linear has x. So it'd be a linear function. So the basic linear function, this would be a slope of 1 and a y-intercept of 0, because we're talking about y equals mx plus b notation, and would be the slope. Slope is 1, so that's up 1 over 1. So basically, it's a perfectly diagonal line right through the middle of your graph. Just like that. So there is f of x equals x. That's our parent function. And now we need to graph g of x is equal to x minus 4. So if you remember back to, I'm just going to write this up top here, y equals mx plus b. M is the slope, which the x is by itself, so the slope is still 1. And then b is the y-intercept, which would be -4, which is where the line crosses the y-axis. So I know you did this last year and the year before, and maybe even the year before that. So we're going to start this one at -4, which is down here on the y-axis. That's that -4. And then from there, it's the same slope, up 1 over 1. So we're going to go up 1 and over 1. So it'll be the same slope, but positionally, it's changed where the location is on the graph. So from our original parent function of f of x equals x down to g of x equals x minus 4, what's happened? What kind? Like, down how many? 4, exactly. So we would describe this as a translation of down 4 units. So this would be a vertical translation 4 units down. All right. Really? All right. Oh, hey, we haven't talked about fire drills yet. So with fire drills, we're going to go down that set of stairs. You are going to exit out that door by Mr. Campagna's room, and then just go to Amaton Field. Stay as a class. I will come out and I will take attendance. So everybody head on down. I will lock the room behind you, so don't take your stuff with you unless you want a sweatshirt. So I did not know this was happening today. This is a complete surprise. All right, I'll meet you all out there. Oh. It was just getting good too.
Thank you. That concludes our fire drill. You may return to your classroom. Thank you.
Okay. Quickest fire drill ever. All right. Well, looks like we might end up needing to wait a little bit on getting your books and all that. We can do that tomorrow, which is fine. Let's go ahead and just keep hammering through some of these questions. We'll get through as many as we can over the next 8 or 9 minutes because that's about how much time we have left. So we just finished up this example 2. There is a word bank over on the left, by the way, but all of these definitions are within the notes already. So let's go ahead and move on down to reflection. So actually, you did all this stuff last year in geometry, like I said, with all the other shapes and things like that. You're shaking your head no, but you did. Promise you did. It was like the 3rd unit of the school year. A reflection is a transformation that flips a graph over a line called the line of reflection. A reflected point is the same distance from the line of reflection as the original point, but on the opposite side of the line. For example, let me grab transformations real quick from geometry. I'll remind you all about what you did. So, translations, there's rotations, where did reflections go? Here we go. Nope, those are rotations. Symmetry. I think reflections was earlier on. All right. Yeah, first one was reflections. So this was one of the assignments from geometry where if you reflect something, a reflection crosses over like an axis or a line of some kind. And so if you reflect something across the y-axis, it's basically like turning a page. You bring it from here to here. You can reflect something over the x-axis as well. That would be bringing something up here and then bringing it down here. So the one that is furthest away here, the thumb, ends up being the furthest away down here as well. The thumb, it's like a mirror image, but it's being basically rotated down. You can also reflect things diagonally. Okay. Here, let's try that. One second. I don't know what's going on here, but it's a little weird. All right, come back. Might need to shut the program down and try it again. Let's see. There it is. All right. That was odd. All right, anyway, heading back to here. You can also reflect something diagonally. So, this one here has been looked across the diagonal axis as well. So those would be reflections. All right. So that's what we're talking about when we're talking about a reflection. So in terms of the next example, a little bit more time here. It says to graph P of X. And it says that that is equal to the opposite of x squared or negative x squared. Graph the parent function as well, and then describe the transformation. So I'm gonna go ahead and get the regular one on here. We'll probably finish up with this one. We'll finish the notes tomorrow. We'll just finish this up tomorrow. Go ahead and start back.
This weekend, D21 is pairing up with St. Mary's Academy on a